So we're going to be beginning to look at association again, but this time it's going to be between quantitative variables. And we go back to our earlier examples where we had at least one categorical variable in the mix. This made things very nice because we could look at the categories as different pictures. In this example, the histograms of the runtime for each of the different genres of the movies. There was only 6 of them, and so we could make an easy comparison between the different genres. And but when we switch to 2 categorical variables, we see that we're going to have a problem. So let's examine the runtime and the budget of each of those 120 movies. And we're just looking at a little bit of the data table here. But if we said we wanted to look at the runtime based on budget, it's true that we would have some repeats in the budget. So there's a couple of movies here that have the same budget levels, but there are lots of different levels. And so we'd have many, many histograms, each with only a couple of different runtimes in them. And that would not give us something that would be easy to compare. So an alternative is to actually plot the data differently and something called a scatterplot. So we look at these different movies and the runtime and the budget, and the idea here is to make sure that we respect the number line for each of the variables by taking a coordinate system, an x and y axis, and putting one of the variables on the x-axis. This time it'll be runtime. Okay, and you see the number line there is in its place. And then on the other axis, the y-axis, the vertical axis, we put on the budget. And then for each of the movies, let's take, for example, Batman Begins here. We'll take the runtime and budget and find where they belong. So, for example, the 140 minutes goes right there on the runtime axis, and the $150 million goes on the budget axis right there. And if we continue over and up from each of those locations, that gets us to a point on that graph where we will put a little dot to represent that single movie. All right. So let's try another one. Let's try Bewitched. You notice it's 100 minutes long and had a budget of $80 million. We find those locations on each of their respective axes, continue up, and then we get a dot for that Bewitched movie. And one more. Let's try Be Cool here, which had 150 minutes runtime and $75 million budget. And so we get a dot for Be Cool. And of course, we're going to do this for all 120 movies, and we're going to get a bunch of dots all over the place, all scattered, hence the name Scatterplot. And from this, we can actually decode the kind of association we have between these two variables. So, when a statistician looks at a scatterplot, what do they want to talk about? And the answer is 3 main things: direction, form, and strength. Say that several times to yourself: direction, form, and strength. Whenever I ask, or whenever you see a scatter plot, you should evaluate those 3 things in your mind. And we'll talk about what those are in a second. But we should also look for outliers and other unusual data that might point to problems or things in the data set that might be problematic for an interpretation of the association, which again we'll see more later. Okay, so let's talk about the direction, form, and strength, each in turn. And for a statistician, we actually have 2 main directions. One is what we call positive direction, which means the scatter of the plot points goes up as I move from left to right. across the graph. This means that the two variables go together in the sense that when one goes up, that one has a high value, the other tends to have a high value, and vice versa. When one has a low value, the other variable tends to have a low value. The opposite of that is a negative direction, right, where I go down from left to right, and what this means is that the two variables are sort of inverses of one another. When one variable is high, the other variable is low, and vice versa. There also is a third option, which is kind of not every scatter plot fits into these two categories, and that the third option is that there's no direction, and this actually can happen in a couple different ways, but one is that there really isn't a direction up or down as I move left to right. It just is a big cloud of points. That's pretty boring. What that indicates is that there is no association between those two variables, and we'll see this in different ways in a minute. But you can also have some kind of pattern which goes up for a while and then goes back down for a while, or goes down and then goes back up, or something that doesn't fit the consistent pattern of going up or down. And so like this scatter plot, you can see kind of goes from a low value and goes up and then comes back down. And so we'd say there's no direction there because it's kind of a mix. Another thing that we want to talk about is the form of the scatter plot, and there again are two main things that we would look for. One is the linearity, or a linear form, where the pattern seems to follow a straight line, and this is the sort of ideal situation. This is the one that we'll focus most of our attention on because it gives us the easiest kind of analyses. But you may also see sometimes a nonlinear form where there's some kind of gentle curve. It's not straight, and so that shows the data has some different aspects to it. This is actually not as bad because there's actually techniques, which we won't cover in this course, but techniques to straighten these out. We actually can make it so that it fits the linear form by doing some manipulation of the data, without losing any information. And then we actually are going to have a third form where if we have a situation where there's non-linearity, but it's up and down, it's back and forth, it's not consistent, that's going to be a little bit more problematic. Statisticians can certainly analyze that, but it takes much more advanced techniques that we won't touch on in this class at all. The third thing is the strength of the relationship. What this means is how closely the data follows the pattern underlying this, the form of the relationship. And so you can see these two graphs here are one is curved, nonlinear, and one is nice and straight, linear. But the data points follow that curve and that line pretty closely. There isn't much scatter around that. So that's a very strong relationship. And what a strong relationship means is that the two variables somehow go together very, very tightly. One variable is a good predictor of the other. Knowing one variable allows you to know a lot about the other variable. So those are very strongly tied. Hence the name. We might actually have more moderate relationships. Strength is really the term. So you see here a nonlinear form. Again, this is one of the not so nice ones. It just sort of goes up and down. And so but you notice there's just a lot of scatter around it, much more scatter than the nonlinear relationship right above. The line that you would trace through that cloud of points, the points are scattered all around it. And here's another one where I have a linear relationship, but the data is kind of scattered around that line. So that is a moderate relationship, moderate strength of relationship. And then, of course, this is a sort of the interesting thing here is that the one variable can predict the other, but there's a lot of error. It's not quite as certain when I say, I know one variable, what's the other one going to be like? There's sort of a lot of scatter of the possibilities. And then the last kind of strength we would want to talk about is a no relationship strength, where there's very lots of scatter of the points all around. And again, I mentioned that this is sort of the idea here is that there's really no relationship at all between these two variables. One cannot be predicted from the other at all, so that we wouldn't be able to use any of the nice techniques that we would have for making predictions. As I mentioned before, another important thing to report about a scatter plot is anything that looks like it lies outside the general pattern being followed by the rest of the points, which is what we call an outlier. And these outliers are going to be almost always are something interesting to look at, and they need to be examined. And it might be the case that there's a problem with that point, that they don't really belong to the rest of the data. They're not part of the same population that the rest of the data came from. But we need to investigate that, because then again, they might be part of the population. Figure what's going on with that data point. So this one right down here, you notice, it kind of sits away from the rest of the cloud of points. So we'd figure out what's going on with there. All right, so let's do a real example. Here's the movies of 2005, and I'm looking at the budget versus runtime, thinking that there is a relationship between those two, right? A long movie probably will cost more to make, and so here's the scatter plot. So how would we describe this? Remember, what are the three things we need to talk about? Direction, form, and strength. What's the direction? Well, as I move from left to right in this picture, and you notice that the points can, in some sense, go up a little bit. The short movies here have pretty low budgets, while the longer movies here have quite large budgets. And so that moving up from left to right is a positive direction, right? And that means that there is some sense that longer movies do cost more and shorter movies cost less, or vice versa. More expensive movies are longer and cheap movies are shorter. They tend to be. Okay. Now, what about the form? This is pretty straight. There isn't really a curve, and I'll just make a caution here that the linear form is what we prefer, and so, like some other judgments that we had to make in the past, we'll kind of prefer the linear judgment by saying that there has to be a pretty obvious curve in the data for us to say something is nonlinear. And since there doesn't seem to be anything obvious in this this picture, we stick with our claim that this has linear form, right? Now, what a linear form means is that the budget goes up the same amount, in some general sense, same amount for each additional minute. We have sort of the same increment of budget. And then the last thing, right, is strength. As we can tell, that if we put a straight line in here, there is quite a bit of scatter, and that means that I should say this is moderate, maybe even a sort of a weak relationship between these two variables. And of course, what that means in this in this specific case is that when I tell you you've got a 100-minute movie, and then ask you to guess the budget, you've got a wide range of movies. Notice all these movies in here are all around 100 minutes long, but some are super cheap down here, almost zero, and some are pretty expensive up here into the close to $100 million range. So it's really not a very particularly strong association between these two variables, even though there is an association. I mean, there does seem to be some tendency where very long movies notice there's no long movies over here at 160 minutes that are less than $50 million, where over here on this side, those short movies, there aren't any that are over $100 million. And so we've got this tendency to go up from left to right. But it's moderate, or weak, we'd say. Okay. Now the last thing, so those are direction, form, or strength. What's the third thing we should mention is the outliers. Does there seem to be any points that seem to be outliers? And there is one right here. It looks like. So what I did, and I hadn't discovered this one until I was preparing this part of the lecture, and said, well, what the heck is that? But right, data point, and it turns out that it is King Kong from 2005, not the original. And here's the data that I found in the data table that I obtained from our book. It said it was 187 minutes long, and it had a budget of $23 million. And I actually was kind of surprised by that. I was like, that's very interesting. That doesn't seem to be. You would think a movie from 2005 it's going to be King Kong with a giant ape. It's going to be a lot of special effects. It's going to be a pretty expensive movie to make. So that seems surprising. So I decided to verify that fact, to verify the facts of this particular movie by going to the Internet Movie Database and looking it up. And sure enough, the estimated budget was $203 million. That's as IMDb reported. So it seems to me that this is one of those cases where an outlier indicates an error in data entry. Somebody accidentally typed in 23 million where they should have put a 0 between the 2 and the 3, and that would have made all the difference in the world. A $203 million movie, which of course would have moved this point up and made it much less of an outlier. So we would have not. And so this is an indicator that looking at outliers can lead to interesting results like data entry errors or things that don't belong. So they should always be investigated. All right, let's look at some other real data sets. Here is a data set for countries around the world, and the data actually is all about costs of living in each of these countries. And there were several metrics about cost of living taken. And two of those, one was the food costs, somehow adjusted to U.S. dollars, and then the cost of women's clothing in each of these countries. And I've created a plot here of those two variables, and what we want to talk about is, what does this plot look like? Well, remember, we need to talk about direction, which in this case, I move up from left to right, is positive, right? What about the form? Remember, form is linear or nonlinear. Does this follow a line? Yeah, pretty much follows a line, right? Don't get too fooled by these couple of points out here. Don't try to curve it to make those 2 points match up to the curve. Look at the bulk of the data, right? And it does look like it's a line. A line would do a decent job. Okay, so it does look like this has linear form. And what about strength? And think about that line that goes through these points. How much scatter is around them? Are they really, is it really obvious that they all stick really close to that line? No, there does seem to be a bit of a scatter in each of those places. Say, for example, all these countries here that have around 450 as the cost of women's clothing, some have food costs way up at 500 and some have food costs way down below 300. So there does seem to be a bit of scatter. So we'll call this moderate. Right? It certainly is stronger than the movies data set that we just looked at, the runtime versus the budget. What about outliers? Be careful. This guy right here, yes, is probably an outlier, but it doesn't. It fits the general pattern, right? It just happens to have a very high cost of women's clothes and a high food cost. We could investigate that one. It turns out that one actually is nothing interesting. So we'll just skip it. Okay. Here's another interesting plot of the same data set where I have the average hourly wage for that country, and versus the hours to earn an iPod, the hours of work you have to put in to get an iPod. And of course, the hours to earn an iPod does depend on what the hourly wage is, but it also depends on how expensive an iPod is, right? So there's multiple factors going into the number of hours needed to work to get an iPod. So when I plot this, we've got to look at the direction, form, of strength, and it's pretty clear. The direction, what's really obvious is the form, but the direction is negative, right? As I move up in terms of the hourly wage, as I go left to right, the number of hours it takes to earn an iPod drops. And that makes a lot of sense, right? Because I mean, if you have a very high hourly wage, well, you only have to work a couple hours to get the money that you need to earn an iPod. But if you have a very low hourly wage, well, the iPods are going to seem less obtainable because you have all the hours you have to put in to get the money to earn that amount. What about the form? As I said, that's obvious. Does a straight line fit this? No way. This is definitely nonlinear. But what does that mean? Well, that means that there's different rates at which these change. So when I go from 20 to 40, the hours that you have to work to get an iPod drop, from 50 down to 25 or so. But when I go from 80 to 100, notice that's a $20 difference, as 20 to 40 is. I don't know actually, by the way, these are dollars, but it's some kind of scale, of relative scale, where 20 to 40 is the same as 80 to 100 because those are 20 apart from each other. But notice the hours to earn an iPod are very low for the 80, and they're a little bit lower for 100, but just a tiny bit lower. So there isn't as big a drop from 80 to 100 as there was from 20 to 40. That's the nonlinear kind, nonlinear form. We note that this actually has the nice kind of nonlinearity. It's not up and down. It's pretty consistent throughout. So there might be a chance of doing some more analysis on this, but not, again, as I said, not in this class. What about strength? It's quite strong, right? I mean, it draw the line through the cloud of points, and there isn't much scatter around that line. So that means that knowing the hourly wage of a particular country gives you a pretty good idea about the number of hours it takes to earn an iPod. And another final example from this data set is the food cost versus vacation days. So how many vacation days a worker gets in that country each year, and then on the vertical axis is the food costs. And what do we see? Well, it's actually a pretty big cloud of points. There doesn't seem to be much pattern at all. So this is actually going to mean that the strength is the most obvious, but we still need to talk about the direction, which we mentioned. When we see a pattern like this, we say, well, there is no direction, right? It's pretty flat and uninteresting. So no direction at all. What about the form? well, there isn't really much of a form at all. We could say that it's linear. There is a notion that, remember that we prefer to linear. So unless we see a curve in the data, we can call it linear. And there's no curve at all. I mean, someone might say there's no line here at all either, but you could draw a line if you wanted to, right? It would be very flat and horizontal. Okay. And then the final thing, direction, form, and strength. The strength in this, it would be, well, there's no strength here, right? There's no relationship between the vacation days in a country and the food costs. Those things just don't have any kind of association, connection between the two of them. And what that means is that, right, so all these things point to the fact that knowing vacation days in a country tells you next to nothing about the food costs.